Hello and welcome to another video for our snow days. This is going to start branching off from geometric series. So this is the warm-up that we would have done, practicing some numeric series, and this is the homework over here. So determine whether or not each of the series below converges. So it's either yes or no by some test. And really the only two tests that you know so far are the Nth Term Test for divergence and you have the geometric test, really for either one, right, depending upon what your common ratio is. As long as your common ratio is less than 1, converge. If your common ratio is greater than or equal to 1, diverge. So the nth term test is the easiest thing to check when I have a numeric series. And remember, it's almost as if you're ignoring the plus signs, right? You're turning the plus signs into commas. And you're just looking at these terms, 1/2, 2/3, 3/4, 4/5, if those terms themselves are going to 0. Since the terms, which I'll just call a sub n because the book does, are not approaching 0, this series diverges by the nth term test. This one looks pretty geometric. I'm just going to rewrite this with the 2 out front and then 1/3 to the n. So this is clearly in geometric form, and I can see that my common ratio is 1/3, and that the absolute value of 1/3 certainly is less than 1. Therefore, this series converges by geotest. This one's a little more difficult to figure out, and I'm just going to go through, just because of the alternating signs, so I'm just going to go through manipulating this into a geometric series so I can be altogether sure. Because it kind of sort of looks, if I look at the terms, man, they're not going to 0. But with the alternating terms, I want to, and just practice manipulation. If I say, I think you can pretty clearly see that this is 5 to the first, 5 squared, 5 cubed, 5 to the fourth. Therefore, I could say that this is a 5 to the 0, yes? Here. So it looks like if I say, and kind of like do like a trick I showed you yesterday, whatever the heck day we were at. Like this 3 kind of is an outlier. So I'm just going to do 3 minus this series. So I'm going to write a series in summation form, n equals 0 to infinity. And if I start at the 0 power, would be this term, but remember I'm ignoring this term, so I'm going to start with 5 to the first. Which would mean if I'm starting at 0, then I would have 5 to the n plus 1. And then I can see that my denominators are powers of 3. And this is 3 to the 0. So I would say 3 to the n. Now that doesn't help me for geometric, because for geometric I need a common ratio to the n, but I can use exponent rules here and say 5 times 5 over 3 to the n. But that doesn't take care of my alternating signs. But again, this is kind of sort of what we did the other day. I'm just going to put my negative in there. And then with my powers that change, this would change. And of course, I'm going to put my 3 minus this series. So I have, put it over here too, minus, no, I don't want to do that. I think you get it. But I've rewritten this as 5 times negative 5/3 to the n. But when I look at my common ratio here, my common ratio, since my common ratio is greater than or equal to 1, this diverges, and if you have 3 minus a divergent system, right, 3 minus something that diverges still diverges. Okay, so there's a nice little warm-up with some numeric series. Now I kind of teased this the last day we were together, where if I go from numeric to replacing the common ratio, and remember the restrictions on the common ratio, right? If you're going to be a convergent geometric series, the common ratio, the absolute value of it, is less than 1. So if I take 1/2 out and just hide it and say instead of numeric, I'm going to replace those common ratios with an x.
All right, will you put your boots and Delaney's boots? You guys are going to sit.
There we go. So all of a sudden now I have a value of x in here for the common ratio, but don't forget that I still just have to remember that whatever this common ratio is, if it's a half, this is a convergent geometric series. Well, isn't it true that if this was a third, I'd still be convergent? If it was 2/3, it'd still be convergent. But if it was 3/2, if I replaced x with 3/2, I would have a divergent system. I'm sorry, a divergent series. So I still have the restrictions that if I want convergent, which as I hinted at before, convergent series are the ones that are interesting to us, the ones that are useful in further mathematics and engineering, is that I want this x to be between -1 and 1, or the absolute value of it to be between -1 and 1. As soon as I replace the common ratio with that variable x, we call this a power series. But I want you to look at the power geometric series as x to the 0 times 1, which is 1, plus x to the first, plus x squared. That's a freaking polynomial. So that's when we take a numeric series and turn it into a power series. I got the power. See that? My little fun icons. So this power series, this power geometric series, and we usually drop the geo and just call it power series, still has an a first term, and an r, a common ratio, and more importantly has an s. This is going to be mind-blowing, right? A for us, r for us, what is s? A is still the first term, 1, r is x, and we're going to put restrictions on x for converging. But s, you ready? 1 divided by 1 minus r, which of course is x for us. Now look at this. Look at this. Hello, algebra 2, right? That's a rational function. This polynomial, now it's an infinite polynomial, right, is the same thing, right? The geo series, if it converges, is equal to the infinite sum 1 divided by 1 minus r. So what I have right now, I have this infinite polynomial is equal to this rational function. OMG, this is actually pretty freaking phenomenal. Because infinite polynomials, true, a little awkward, they're infinite. But you know what? What if all I need is an approximation? If I chop this infinite polynomial off and make it finite, it's no longer exactly equal to this rational function, but it's pretty freaking close, right? And I want you to look at this right here. Hello, tangent line, right? Linearization. Hello, parabola. Opens up, y-intercept at 1. Plug in 0 for x, you get 1. Hello, cubic function. I know what that end behavior is like, right? From linear function with a positive slope to quadratic with a positive dilation factor to cubic with a positive dilation factor. I mean, OMG, I know a lot of stuff.
Sure. Boy, you're pretty strong. So Delaney took a picture of you and won a medal? A certificate? Yeah.
I know a lot of stuff about polys.
Grotesque? To be most grotesque.
Now, I do need to talk about the interval of convergence. That's just a fancy way of saying what we know about geometric series. This is just asking what numbers can you plug in for x and have convergence. Interval of convergence. Well, isn't it true that if my ratio had been a half, and if 1/2 absolute value of was between -1 and 1, I would have convergence. Well, what is R now? It's my x. So as long as I replace x with any number between -1 and 1, not inclusive, can't put in -1, can't put in 1, I will have a convergent series. And that infinite series is equal to 1 over 1 minus x in this case. So an infinite sum of a geometric series can be represented two ways. Here's a screenshot of 1 over 1 minus x. I hope you can clearly see the asymptote right here, right? So what I'm saying with the interval of convergence is that here's my asymptote at 1, here's -1. So look at the function in between there. Here's what 1 over 1 minus x looks like with every x between -1 and 1. That's what it behaves like. With the infinite sum being with that infinite polynomial being equal to 1 over 1 minus x, what if I look at the graph? If I look at the graph of this infinite polynomial, which is impossible, so I have to make it a finite polynomial, I will then get close to the graph of 1 minus x, provided that I stay within -1 and 1. So as long as there's x's in here, what I'm saying is that this infinite polynomial will match that yellow graph exactly. Right? So I can't put an infinite in, but if I put as many as I can, we can see this. So what I want to do is I want you to get out your calculator, and I'm going to do it as well. And I want you to make your window the interval of convergence. And then we only need your y-mins to go from -5 to 5. So I'm going to switch programs here. And you can see in y1, I've put 1 divided by 1 minus x. And then I've put the first terms of the geometric series in here. This is a times x to the 0, a times x to the first. Notice that I've made this a bubble, right, so that it traces just a little bit slower. So I'm going to hit graph, and I made my window -1 to 1 and 1, and my y is -5 to 5. And I'm going to hit graph, and you'll see the rational function in between -1 and 1, and then here comes 1 plus x. Now look, it doesn't match here, right? But as you can see, as x gets really, really close to 0, it matches, but then as I go to the right of 0, I start to go away from the function. So if I hit trace, right, you can see that as I go left, versus if I go right. Actually, you know what might be easier is let's do the table. Let me change table set to ask. And if I put in 0, I want you to think about the polynomial is at 1 plus x, and the rational function is 1 divided by 1 minus x. So what happens if I put in 0 for x? This is 1. Both the rational function and the polynomial are exactly equal at 0.
With liners?
Yes.
Where you have liners now?
If I go just to the right of 0, though, if I say 0.2, maybe, then that's not exactly alike. If I put 0.4, not 0.5, 0.9, right? Way off. If I go left, right? And you can see that the error on the left, as I go the same distance left of 0 and the same distance right of 0, the error isn't balanced, but that at 0, the linearization function, right, at the tangent line, is exactly what the curve is. And again, you can kind of see that on the graph. So what happens instead of a linearization? What if I add another term? A r to the 2. This is a quadratic. There's the rational function on negative 1 to 1. Now notice how well the bubble matches the curve till I go, oh, not so good. Look at the error here, right? A lot of error on the right, not as much on the left. Again, if I go to second graph, still at the point of tangency, the quadratic function matches the rational function. As you go to the right, right, less and less, to the left, what happens if I get the quadratic of best fit? Whoops. Ah, sorry.
Just bring one that's half used, half closed. There might be some up here too, though.
So there's the cubic. Again, there's the rational function. Now watch, the cubic will come from under, right, because of cubic behavior with a positive leading coefficient. Again, the more and more terms that you add, as long as you stay from negative 1 to 1, the power series, the finite power series, will get closer and closer. And the infinite series is, of course, exactly the rational function on that interval. So the infinite sum that we've been working with of the geometric series with a is equal to 1 and r is equal to x can be represented by the rational function as long as you stay between negative 1 and 1. Do I want a rational function or do I want a polynomial? We love polynomials. So this is the process I just took you through. We graph the tangent line or the linearization of the rational function at 0. Right, because the function, when you put in 0 to the rational function or to the infinite sum or into the infinite polynomial, you got the same value. That's called being centered at 0. The rational function and its approximations, because remember, only the infinite polynomial is exactly equal to it. So every time I chop it off, I'm approximate. But at the center, fact will equal fiction. right? If you plug in 1, I'm sorry, if you plug in 0 here, you get 1. If you plug in 0 to any of the approximations. There's the quadraticization. These are made up words, of course. Cubicization. Fourthization. And we looked at the table to verify that on our calculator. So let's do another one. We're going to find a power function that represents, or a power series that represents this geometric series and the interval of convergence. So we have two things to do here. We need to find a power representation, and we have to find the interval of convergence, often approximated as the IOC. So this is a geometric series, right? And I'm just going to rewrite it so that it looks a little bit more familiar to me. And I only do this because I saw it, because your book presents it like this sometimes. So I write it like that. I think of forgot that I wrote this down. Let me erase my writing. Right, A, which is 1. R to the 0, A, R to the first, A, R squared, A, R cubed, right? This is my geometric series, but what is R? My first term, when you put in 0, is 1. My R is 3x, so what is the infinite sum? Formula doesn't change. 1 divided by 1 minus, but this time my R, right? My R is 3x. And what do I need to make sure of? That the absolute value of R is less than 1 if I'm interested, which I am, in convergent series. So I just do a little algebra and divide both sides by 3. So if you can do this on your calculator, I'm not going to go through the calculator this time, but if you type into change y1 to 1 divided by 1 minus 3x, and then put into y2 1 plus 3x, that will be the tangent line, again, at 0. If you put in 1 plus 3x plus 9x squared, you will see that the rational function 1 divided by 1 minus 3x is exactly the same as the quadratic 1 plus 3x plus 9x squared at 0, and then starts to, as you move to the right of 0 and to the left of 0, there's error in the quadratic. And you can add the cubic. You can add the cubic term, right? Make 1 plus 3x plus 9x squared plus 27x cubed would be the cubic curve of best fit, if you will. All centered at 0. So this infinite polynomial is exactly equal to this rational function. And we say that this is centered at 0 because 0 is where the polynomial, you can chop off at 0, and you don't need all the rest of the terms. If you plug in 0 for x, you will get exactly 1 divided by 1 minus 3x. So I wanted to do this one with you because it's a little weird with the alternating term, right? It's just a little, algebraically can cause you some confusion. So I'm going to write it this way and think of my R. And the reason I do this, I hope this becomes clear in a little bit. Remember, we had the series that we were working with before was either 3x or, right, we had like 3x to the n, and we said this is centered at 0. This one is not going to be centered at 0. Can you guess where the center is? And that's why I kind of leave it in this form. So I'll kind of leave that hanging for a minute. So I'm going to calculate the infinite sum. And remember, the infinite sum of a convergent geometric series is of the form a over 1 minus r, right? And this sum is a rational function. So what is a? What's my first term? My first term, when I put in 0, right, I get 1 over 1 minus r. Now my r is negative 1 times x minus 2. I'm going to distribute my negative in here just to make this look a little cleaner. So I get, right, negative x plus 2. So I'm going to write that as 2 minus x, right? Which of course then is 1 minus 2, which is negative 1, and plus x. So my IOC, I can either use this version or this version, it matters not. Remember, I'm going to put r in here. And I'm going to do some algebra, right? And I'm going to subtract 2 from both sides, so I get negative x. 1 minus negative 2 is negative 1. Oh, I have to divide by a negative, which remember means that I switch the inequalities, which that's awkward. You can't write it like that. Now, remember what I said about the center? Just think about this on a number line, right? If I have 1 here and I have 3 here, hello, what's in the middle? 2. Not a coincidence, right? Which is why I say I wanted to leave my r in this form, because as we'll see for power series, where is it centered? At this value. So if I had a power, if my ratio was x minus 0, my power series and my infinite sum are exactly the same at 0, and then the error starts to radiate out from that. If this was 10, my center would be 10, and the polynomial and the rational function would be exactly the same at 10, and then as you moved right and left from 10 through the interval of convergence, right? This of course doesn't match, right? But if I had a center of 10, I would have an interval of convergence around it. For us, our center is 2. So can you guess, Algebra 1 kids, if this had been x plus 2, what your center would be, right? So, but when I start to construct the power series, I'm going to drop this version, really, into it. Oh, sorry, so I thought I wrote it out. So I'm going to write this as 1 times negative 1 x minus 2 to the 0, negative 1 x minus 2 to the first, negative 1 x minus 2 squared, and so on and so forth. And then I'm further going to do this. I'm going to drop the 1's now. I'm going to say this is negative 1 to the 0 times x minus 2 plus negative 1 to the first times x minus 2. Now you'll notice when I put this in the calculator, I actually revert back to this. Okay. So let's look at this on the calculator. Oh, before I do that though, let's clean this up. So this is 1 over, right, 1 minus 2 is negative 1, and then this is plus x, right? So this is 1 over x minus 1, if I did my math right. So we are saying that 1 over x minus 1 is equal to this infinite series. So I'm going to go to the calculator. Come on, calculator. So I'm going to put in 1 over x, whoops, x minus 1 and now in here I'm going to put 1 plus 2 minus x to the first plus 2 minus x squared plus, oops, 2 minus x cubed. And I've got to go change my window, right, to my interval of convergence, which is 1 to 3. Rats. One, two, three. So there's the rational function, and here comes, oh, gosh darn it. Did something stupid, didn't I? What did I do wrong? One plus 2 minus x plus 2 minus x. Redonkulousness. Sorry, kids. We're going off snowboarding in a little bit. So I only put in to the quadratic, so here we go. You can see that it is exactly equal at 2. And look at the error on the left this time. The error on the left is much big. The error is much bigger than the error on the right. Let's hit our table. And you see this time if I hit 2, right, when x is equal to 2, the rational function and the quadratic approximation that I put in are exactly the same, but as I start to move away from 2, so if I go to 2 calculator's messing up. So I hope you can, if I went 2.1 or 2.2, if I went to 3, or if I went to 1.9 or 1.8. But right now this is not working well, so I'm done with it. So here's the thing that's even crazier. That example that I had, I'm going to actually do some calculus. Whoa, you didn't see that coming, did you? So here's the function written out again. Here's in geometric series or summation notation. This is the rational function, right, using the formula for the sum. Here is equal to this infinite polynomial. Well, I hope you're sitting down because this stuff is crazy. I have an equation. I can do what I want to one side of the equation as long as I do the same thing to the other. I'm going to take the derivative of both sides. Okay, so I'm going to focus here first. We're going to do this first. Don't worry about doing integration yet. So I'm going to take the derivative of 1 over x minus 1, which means I'm going to take the derivative of this polynomial. But how easy is that? Remember, this is a constant, right? What's the derivative of a constant? 0. This is a constant times a function. What's the derivative of a constant times a function? Well, it's that constant, check, times, how do you take a derivative with a chain rule, right? You bring down the 1, here's the 1, copy over the middle, subtract 1 from the exponent. Don't forget the chain rule. You are actually spitting out the derivative of x minus 2, but that's 1. So that's why in this version I didn't use the, remember, because I could have, which I did in my calculator, I could have used 2 minus x, right? Would still take care of alternating my powers as I went through. But if then when I took the derivative, taking the derivative of 2 minus x would involve spitting out a negative 1, and it would all end up to be the same, but just my algebra would be messier, I think. So that's why I preferred to leave it this way. So what am I doing with the next term? I'm going to take the derivative of the next term. This is called term by term differentiation. Right? So take what's the derivative of a constant times a function, that constant, bring the 2 down in front, copy over the middle, subtract 1 from the exponent, spit out the derivative of the inside, which is just 1. What's the derivative of a constant times a function? That constant, bring the 3 down, copy over the middle, subtract 1 from the exponent, spit out the derivative, which is just 1, etc., etc. Now notice I haven't actually taken the derivative of the left side yet. There I go. So here's another whole rational function. This is negative 1 over x minus 1 squared. That I have an infinite polynomial representing this rational function, right? This has a power of 1 on it. This is crazy, right? And again, if I just want an approximate, well, I can use the tangent line approximation, the quadratic approximation, the cubic approximation. Look at this. Look, if I go backwards, if I said, wow, here's this sum over here, right? Here's a sum. Can you represent it as a, trying to change my color. Or whatever. Can you put it back in summation notation? So looking at this term by term, how do you describe it? Here's the alternating term. Here's the summation notation. But check out this. Right? How do you take the derivative of this thing? Power down. Bring the n down in front. Check. Copy over the middle. Check. Subtract 1 from the exponent. Check. Multiply by the derivative of the inside, which is just 1. OMG. The interval of convergence and the center of the power series that you got by differentiating is the same as your original. Right? So this power series here, infinite power series that is exactly equal to -1 over x minus 1 squared, has the same interval of convergence, and which was what? For us it was 1 to 3, and the same center. I guess I shouldn't call it, I'll call it C for center. Okay. So now let's do the integration. This is even wackier. All right. If I want a power series to represent the integral of f of x, and remember f of x was way back, right? Here was f of x right here, and here was the power series representation for f of x. Now I want a power series to represent the integral of f of x. And you're always going to start at the center here, and you're going to go to x when you're integrating, so that's why I have to use my dummy variable. Right? So just like I have an equation, so I'm going to integrate the left, and I'm going to integrate the right. So notice that this is, here's my center of 2, and I'm going to go to x, and I replaced x with the t, and I'm going to integrate dt, and I'm going to integrate this infinite polynomial from 2 to x, right? So using the second fundamental theorem. So just this is term by term anti-differentiation or integration. So how do you, what's the antiderivative of a constant, right? It's kind of, think about this constant sucking out front, and then this is power up. Add 1 to the power, divide by that power, that new power. So that's why I have t minus 2 to the first over first. Suck this power out front, integrate, add 1 to your power, get 2, divide by 2, check. And just keep all the way along. Now when this is how I'm going to, I don't really write this stuff out much, but it will be important later. So what do I do now? I put in x replacing t, right? So I put in x, 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 and then I subtract when I put in the center, 2. What happens when you put in 2, 2, 2, and 2, right? You're going to always get 0 there, except for that. But look at this. What is the integral of 1 over t minus 1? It's ln. Oh my God, that was natural. Mwah. I have a natural log function that is exactly equal to an infinite polynomial. A polynomial. Now again, I can't graph infinite or plug in values into an infinite polynomial, but I can get a darn good approximation to this ln function with a polynomial. You know when you hit that ln button on your calculator, how the heck does it come up with an approximation? How do you think? It's got power series representations for ln in your calculator. Again, as long as I stay within the same interval of convergence, which for us was between 1 and 3, and I know I'm exactly the same at 2, the center. This is wacky stuff. Wacky stuff. And again, here is the summation notation. Notice the relationship from where I started. Whoops. Where I started, how do you anti-differentiate? Again, you take this constant, suck it out, osmosis it out front, right? And then I just put it back. But how do I anti-differentiate something to a power? Power up. N plus 1 divided by n plus 1. So now what if I ask you to go backwards? Okay, so something else that your homework might ask you to do. I will give you the rational function, and can you go backwards? So this isn't so bad after that differentiation and anti-differentiation. If I give you f of x, and I want you to think of that, remember, as the infinite sum of a geometric series formula, a over 1 minus r. Right? Check. So what is the series generated from that? A, right, the first term with the power of n, r to the first, r to the second, r to the third. The interval convergence, now please, that's me smart. I've seen very, very smart kids do something silly like this. Well, this is like this, so that's x. This is like this, so that's 1, and this is square root of negative 1, doesn't exist. Come on now. What am I asking? What values can you square and stay between negative 1 and 1? Right? That's what I'm asking. And those are the same values that if you put in for x will stay between negative 1 and 1, right? So for instance, think about negative 1/4. If I put negative 1/4 in for here, in for x, I square it, will I be between negative 1 and 1? Yes. If I put up 1/4 in here, will I be between negative 1 and 1? Yes. So here's my IOC. What if I throw you a curveball and make this a plus? What's that going to change? You just have to realize that your r, right, you have to be in the a over 1 minus r formula. So that will just change what the series looks like by alternating its signs, right? But it won't change the interval of convergence. So your homework problems tonight, hi, you see me in my snow gear, will be, again, from the beginning of this slide, beginning of this PowerPoint, and the PowerPoint I'll put on Edline as well so you can look at. We'll be asking you about taking geometric series and turning them into power series or vice versa, and could ask you to differentiate term by term or anti-differentiate term by term. And then on Monday we will do practice problems on both numeric and improper integrals and geometric series to power series before we move on. So I think that's it. See ya. I'm off to Whitetail. Bye-bye.